Welcome. Greetings, Singularitarians. Thank you for joining us here today. Good morning, good evening, good afternoon, wherever you're joining us from. It's so good to have you here. So excited to be back for another excellent Technical Tuesday and to be joined by Barrett Cook, one of our AI researchers, and something of an AI lead for the coordination with the Sophiaverse project as well. So that's very exciting. We'll see if we can dip into that just a touch and how this work applies to Sophiaverse progress as well. But today we're really going to look at the AIRIS system, so overcoming the limitations of reinforcement learning with a live AIRIS demo. And I'm very excited to have you here today. Thank you, Barrick.
Thank you. Thank you for having me.
Yeah. It was amazing to meet you in person at AGI 24. It was an amazing time. We've just been talking about what an amazing conference, what a cool conference it is. It's a very tight knit group of people that are looking in this direction of very advanced AI systems, philosophically, ethically, technically, mathematically, and how all these things come together. And this was one of the stars of the show for sure. Seeing this demo and the interest that this generated. Both we've had this interest from SingularityNET, from the NARS teams, from Patrick Hammer and Peter Isiev, and as well as from just the general attendees as well. So, can you introduce this system a bit? What's special about it? How it contributes to AGI, and what's whizzy and unique?
Yeah, absolutely. I had the privilege of demonstrating this system at the AGI conference. Unfortunately for our live attendees, that was not something that they could see. So we kind of got our heads together and thought, well, why not just do a Technical Tuesday about it? And so this system is a experiential learning system that creates rules from observations and uses those rules to create kind of like a action state map of different actions that result in different states. And it dynamically learns these interactions and adds to the rules and modifies the rules. So it's a very adaptive system. It can learn how, in the example that I'm going to show, it can learn how to navigate and move around in like a Minecraft world or other such things. The early versions of this system were done with just simple 2D grid worlds. And so now we're kind of expanding on that. We want to bring it more into like add a third dimension to the system and add it in a kind of a continuous environment instead of just this discrete movement type thing of a grid world. Because what we really want to do is we want to eventually expand these systems to work in the real world. We want to, address the complexity of the real world and of the continuous and kind of varying environment that we live in. So for this demonstration that I'm going to show today, I'm going to, first I'll fire it up here. On the left, you're going to see the Minecraft world that a normal player would see. And then on the right, we're going to see what the Minecraft agent itself sees, which is a little bit different. So right now, it's mind space. It's just this kind of like empty void because we're starting it off fresh. It hasn't learned anything. It has never seen this environment before. The only thing I did was I manually added in a little diamond block here that's going to represent where I want the AI to go. So this is like the goal of the AI. Get to this diamond block from wherever you are in the world. Oh, it's doing a little crazy spin here. Let's stop that. Okay, so first thing I have to do before we even get started is make sure that it can get to this location, because although Minecraft does have static worlds that we can just call and have, call a particular seed or something like that, there are variations in the seed that can cause problems. Like there are different, the trees can grow different forms of leaves, which can sometimes clear path and sometimes block the agent. So there's a bit of randomness involved in this test. And what we're going to do is we're going to, in a second here, it's going to teleport itself to its starting location and do what one particular young attendee at the AGI conference has dubbed the startup sequence. And I love that. That was great. So the startup sequence is where the agent first explores what it can do. So it's first testing out all of the different actions that are available to it. And we're going to see if we can, there it is. So way over there, that's where it's first learning. And this is where we want it to go. So I'll pop over there real quick so we can get a closer look. So what you're seeing here is it performing all the different actions. There's 16 actions total. So move in one of the directions, like forward, backward, left, right, and then diagonally in all 4 directions. So those like the 8 different directions that it can go. And it can also jump in each of these different directions. So a total of 16 different actions it can perform. And as it is performing these actions, it's looking to see how its inputs, because this is a representation of the inputs that it's seeing. It's seeing how its inputs are changing, you know, what new blocks it's seeing and where its position is changing to. And so what you're seeing here, that blue box that's around, the big blue box that's around the little blue box, is its view. This is the like a cube of the block names that are around it. So it's not seeing like we see. It's not seeing all of that visual data of the whole world. It's just seeing a little cube of grid cube of the different block names around it, like air blocks and grass blocks and dirt blocks. And that is what is are the type of inputs that it's seeing and how those inputs are changing as it's moving around in the environment. And now that it's finished doing its startup sequence, it's starting to make some plans. So what we're seeing here is the little blue boxes are where it is. The black boxes are where it has been. And we'll see that a little later because it's kind of off exploring right now. But the green arrows that we're seeing is the direction that it's trying to go, where it is anticipating it's going to go. And if there's no box in the spot where it's trying to go, it's predicting that this is how the world's going to be. I'm predicting that I'm going to move forward in that spot, even though I've never been there before. And so now it comes up against one of its first challenges, which is just stuff in the way. And it's kind of seeing how, when the different actions that it's performing, how those actions, depending on what blocks are around it, are affecting its ability to move. And so it's learning kind of like new rules as it's doing this. Like, oh, there's a tree. So if I move kind of sideways against the tree, I'm going to slide against the tree. And if there's blocks in front of me, I'm going to have to jump to be able to get over them. If there's like an empty space in front of me, I'm going to drop down when I move instead of just being able to walk through them. And sometimes it'll experiment with things like, can I move through this block, right? It's like, I think maybe I can move through this. And then when it jumps, it's like, oh, okay. So when I jump against this block, then I'm going to hop up on top of it. And there's lots and lots of rules it's creating, right? For the completed total of this particular test, it creates almost about 600 rules. For different configurations of the different things that it's seeing, because there's a lot of different ways that moving in a dynamic environment like this affects it. The commands that it is sending are not move to this particular grid location and then stop. It's just move for this amount of time and then send a command to stop. So there's some variety there that can interfere. Well, I shouldn't really say interfere, more like cause some confusion, right? So sometimes when it moves in an open space, maybe there's a little bit of lag and it moves 2 spaces instead of 1 space because the command to stop just didn't quite get there in time. So it has to adapt to all these variations and all this uncertainty that is happening in the environment, which is actually kind of interesting from the longer term perspective of what we want to do, which is to put this into a robotic form. Because in the real world, there's a lot of uncertainty, right? You can send a certain amount of torque to the motors and expect it to go a certain distance, but if it's on a carpet, it's not going to go as far. You know, if it's on a slick floor, maybe the wheels are spinning or something like that. So it has to be able to learn, okay, I'm in this situation. I have to adapt and understand that I'm not going to go as far as I think I'm going to go if I was in a different situation. So I have to learn these new rules and be like, okay, I really have to spin these wheels to get some traction, to get moving on this ice or whatever it's trying to navigate on.
So we have
Actually,
an
let's.
agent, we have a world, we have a goal. It's got a diamond block that you've put on its world map, kind of
Mhm.
arbitrarily that it needs to get to. And now it's just navigating in this world to learn about it with curiosity. Can I move through a block that is leaves? Can I move through a block that is trunk? Can I move across a block that is grass? Is that's accurate, correct?
Yeah, exactly. And so as it learns these rules and it encounters obstacles and things in its way, it's kind of adapting these predictions to be like, okay, if I'm up against, like for this tree example, if I'm up against a tree, I'm not going to be able to move through these leaves. It's going to like push me. If I'm at an angle, I'm going to have like slide along these trees, or I'm going to slide along these leaves. And so there's definitely some variation that happens. And as it's learning these rules, it's getting better able to predict what the outcomes of its actions are every time that it encounters something new. So if it encounters a new situation that it hasn't seen before, it would be able to predict accurately how it's going to move around or have to navigate around this particular object or whatever the challenge is that's in front of it.
And
So
this
in
is
this,
this is significantly different than reinforcement learning, where for Minecraft with reinforcement learning, you need to have human game players play thousands of hours, hundreds of hours, whatever it is of games, so that an agent can learn how to move, what it can do, what it can't do, how to get out of a hole, how to get up a ledge. Is that correct?
yes, exactly. So with like traditional reinforcement learning, like you said, you have to feed it lots and lots and lots of training data, right? It has to be able to observe many different variations, many different of the same type of environment over and over again, either through human play or through gameplay itself. There's different variations on how it can learn these types of situations, and it's also very brittle. You have to have trained it in this environment. It can't just go off and explore some part of Minecraft that it hasn't seen before. As soon as it goes off of the beaten path of what it has been trained on, it fails. It breaks down and is unable to learn or figure out what to do. Because that's the other thing about reinforcement learning is that once you have trained a model, it doesn't learn in real time. It's not like it's something that is adaptively learning and online learning all the time. You've trained the model, you kind of freeze that and then let it run to see how it does. Whereas a system like what Iris is doing is dynamic. It is learning on the fly. It's always learning. And it learns very quickly and is able to just like we're showing here, just freely explore and see how the world works and kind of soak in all of this information. And as the more information that it learns, it is better able to navigate. It's better able to predict what's going to happen. Um, and actually, let me pop over here because this is a pretty good example right here. Because what it has done here is run into kind of like a tree trap. These leaves are too low to the ground for it to be able to just walk through. So it is having to learn, okay, I can't walk through these leaves. I can kind of jump and move it around. And it's exploring to see, okay, how are these interactions working? When I move in these certain ways, how am I is my expected result going to be? Like, where do I think I'm going to go? And what we're seeing here is it making plans of things to try in the environment, movements that it is expecting. Okay, I've been in this spot before. I think that if I do this particular action, I'm going to end up back in that spot. And then from there, it's like, okay, what can I do from there? I haven't been there before. Let's try and see some of these things. And we can actually see in a couple of cases here where it understands enough about the interactions that it's doing to be able to predict that even though it hasn't been over here, it will be there when it performs that particular action. And so it's kind of probing and exploring this little space here. The white boxes that we're seeing here is it searching its state space, like its internal map or memory of the world, to figure out, okay, I've been in these spots before. I know how to get back into these spots. What actions can I take from these spots that might result in moving forward or progressing towards my goal? Because what I'm doing now is I'm kind of beating my head against this bush and not really getting forward. I'm not making any progress towards my goal, which is not too far away. I can zip over here to the goal, and you can see at this point it's traveled all the way over there, and it's kind of heading towards this way. So it's getting pretty close to its goal. But it's having to figure out how these different interactions work and figure out, okay, what states can I go to that might result in something interesting happening? And here you can see it. It's like, okay, I think it didn't know that it could jump up on top of trees, and now it jumped up on top of a tree. And it's like, okay, from this little state that's right down here, I can jump up on this tree. But knowing what I know about what I've seen, what else can I learn? And so it's experimenting with the different actions that it can perform to see, okay, can I move through leaves if they're up here, like not directly below? If I'm standing on leaves, can I walk through leaves? And it's learning, no, that's not really how that works. And so it's kind of
So it
exploring.
recognizes this as a distinct state. I'm now standing on leaves. I'm no longer standing on grass. So maybe something behaves differently than it did um, previously.
Yeah, exactly. And so as it's learning this, it's figuring out, okay, now I can hop over these trees just like this to be able to get around this wall of trees and be able to continue on exploring towards my goal.
Now, I have a question. I don't mean to make it sound trite or anything, but
All right.
when it got stuck in the tree space, is that
Mhm.
now a square it will kind of avoid because it's like I couldn't find any way through here, so I'm not going to go back. Like my Roomba would find that spot and explore it all day, right? And then if I push
Right.
it out, it would go back in. If I push it out, it would go back in, right? Like it would
Mhm.
keep going back to that spot where it got stuck.
Right. And what this system does currently is it's kind of like a balance between exploration and exploitation, right? That's something that is common in artificial intelligence of any kind. It's like, how do you use the knowledge that you've learned? Oh, and it just fell down a big hole, which is going to be a challenge for it to get back out of. But so it's trying to see, okay, I'm exploring, but I also have knowledge of what I've done in the past. So if I was to reset it all the way back at the beginning, it would get to this point, and then it would just hop. It knows that it can get over the tree, so it would hop over the tree just like it had before. Unless there was something like maybe something along the way where it moved in a different way and ended up like over here, then it might explore and uh, discover that there's a way around the tree rather than hopping over the tree, which is a little more intensive. So here, as it's exploring this cave, it's kind of moving towards its objective, but it's seeing, well, yeah, I'm moving towards this diamond block, but I'm also moving down away from the diamond block. So that's not really, this isn't working. I don't really want to explore further down this way because so far there's not good progress there. So I'm going to branch out and kind of explore off to the sides and see what other, because it just has a very tiny slice of this environment. So it has to explore out and see what's around me. How can I see what's around me to maybe get me closer to my goal if I backtrack rather than try moving forward and keep going down. So there's a potential for it to even go further down the cave as it explores off to the side like it's doing, if it can't find a way like up the sides to get back up to the top. So there's a lot of different variations. Like I said, depending on the lag of the inputs, sometimes the movement commands are slippery. We can say that. So there's a lot of things that it has to learn, especially about moving and jumping in a in this kind of layered multi-block type of situation where it's because its movements aren't exact and it's not moving from exactly one block to exactly another block. A few times you can see where it will land where it's half hanging off of some block in midair, and it found itself in this state. And it's not it in next time that it moves in a down into, say, somewhere down here, it might revisit that state to try and get back to that spot, and it might get there, it might not. It might fall off that edge if it moves too far or something and end up in a different location than what it has already experienced.
So it's
And
made a rule that may apply, may be faulty, right? If I jump from a stone block to a grass block, at
mhm,
a diagonal, then I'm going to hang in midair, and it has to test that
yep,
assumption.
yeah, and so exactly, it's testing that assumption to see if that's accurate. Um, And if it is, that's great. It will reutilize that information and move in that same way. If it doesn't, if it falls somewhere else, well, then it kind of updates its rules like, okay, maybe it was just coincidence. Maybe it's just a one-off thing where I happened to land in that spot and I don't know how to get back to that spot now because what I thought got me back to that spot didn't work this time. And so it has to kind of adapt these rules and adapt this information as it experiences the world around it. And as it is exploring, it's looking for ways, just like it was doing with the more simple challenge of the tree. It's trying to figure out a way. Okay, how do I get up from here? I'm down here. How do I get up? And it's exploring and seeing if there's some path that it can find. And it also has to learn how these new block configurations affect its movement. Like that, how does moving in an open space make it fall down? And if it does, okay, that's great. I'll remember that and try and incorporate that into future observations. Because all of these rules, it's constantly checking that box that we're seeing of its view. It's constantly looking and saying, okay, how close is what I'm currently seeing to one of these rules that I made, any one of these rules that I made for a particular action. And as it's doing these checks, it's looking to see, okay, I think this is the most similar to this particular rule, which means that I'm going to move in this particular direction in this particular way. And whatever is the closest matching result to this search of its rules, it'll predict that that's what's going to happen, whether that's true or not. And so, because this thing has only been alive for 20 minutes, it has not had a whole lot of world experience yet. And so a lot of its predictions are wrong. Some of its predictions are getting more accurate. It's anticipating that jumping in a particular direction will result in a particular outcome. And sometimes those predictions are right, and sometimes they're slightly off. And so it's having to figure out all of these different ways that its actions are changing, and the way that the configuration of blocks around it affects the outcomes of these actions.
These
So it
white
has
that
a lot of learning.
the white that just flashed on there was showing where it feels confident it can get back to. I know how to get to these states and repeat actions
Mm-hmm.
there.
Yep. And if it's black, those black ones are places it knows it's been, but it doesn't know how to get back to necessarily. Its predictions of the actions that it takes don't connect to any of those particular states yet. And so as it learns more, like here's a pretty good example, it starts to make longer plans where it can say, okay, I'm here. I want to move along this green path and see what happens when I jump upright. I think I'm going to end up in this nice little alcove. Of course, that's not what's going to happen because it's still learning that the configuration of blocks are important, and some will let you move in certain ways and some won't. But it's also trying to explore and see places that it hasn't seen before to see if there's an easy way. right? It's not like it's looking, okay, how can I explore to be able to exploit the knowledge that I already have? So
It
it's
seems
really
like
interesting to watch.
it must have created a lot of rules by now, right? It's been over quite a bit of world, a number of different blocks, perhaps not
Mhm.
as complex as a human world, but still, how does it, and it's still moving very fast. How is that, what's the process for streamlining that to make sure that it's able to check against all of the rules that it's generated so far and not get bogged down in
In the
complexity
combinatorial
and the
explosion, right?
explosion? Yes.
Yes, yes, exactly. Because you're right. It has, at this point, it's probably made a couple hundred rules, at least. There's a couple of factors that go into the optimization of that. One is each rule is tied to a particular action. If it's planning on performing a particular action, there may be 10, 20 rules associated with that action. So it only has to search those 10 or 20 rules for that particular action. And then it does have to search out all the 16 different actions that it's doing. But because it has this memory, it has a memory of where it's been and what actions have done what, and that memory stays. It is able to, just as it learns new information, as it learns new rules, when a prediction fails, when it thinks it's going to do one thing and something else happens, it has to create a new rule for that and be like, okay, I thought this was going to happen, something else happened. Let's make a new rule that says, okay, in this particular situation, this will happen instead. And so it has to not only search all of these different rules, but also has to update them with information as it's doing it. And as it is updating these rules, it's keeping those same lines of prediction that we're seeing here, where it's predicting out all the different things where it thinks it's going to go. It's keeping those predictions in its mind of like, okay, I think that that's going to happen from this particular state. And then when it updates these rules or creates new rules, then it just reevaluates those particular actions across the entirety of its knowledge, of its experience, for all, well, at least the ones that it can search at that time. So as it's searching out these spaces and these little white squares, it's updating all of those predictions with new rules information. And most of the time, that doesn't affect anything. That doesn't change the outcome of those predictions. But sometimes it does. And it's those sometimes that it does that make it able to move forward and adapt to new knowledge, and use that new knowledge to continue to build out a better prediction graph, if you will, or predictions of what's going to happen. And already we're starting to see a little bit of that, where it's starting to make pretty decent predictions about what's going to happen. Of course, right there was a moment where its prediction failed because the jumping process of jumping and then stopping wasn't quite exactly accurate.
And so this agent, it can't mine, it can't place blocks. It's just a movement agent.
Yes, that's correct. Yep. Um, so it is only able to move around right now. Part of the reason for that is I originally gave it the ability to mine and destroy blocks. And one of the things that it was curious about was what was underneath it. And so it would dig and it would dig and it would dig and it would, expand. It would kind of start to honeycomb the area around it, because it was like, I don't know what blocks are over here. Let's go explore, and I can get there easily. So there's definitely some planning. Uh, well, I should say some planning and reasoning improvements that are necessary before we can give it the ability to manipulate the world around it. And otherwise, it will just keep doing this exploration. And part of that is making it, is requiring some effort, right? So requiring effort like maybe you'll see sometimes when it's moving on flat ground and it'll jump on the flat ground instead of just moving. So jump requires more effort. So maybe it needs to take that effort into consideration. Mining blocks takes time. It takes effort. And so instead of just, easily breaking the world around it, it would be easier for it to maybe break a couple things that were in its way rather than just, exploring out the whole the what's underneath its feet.
It's very interesting to look at the, dedication it has towards reaching that block on a direct line, like, "I need to get through this trees, I'm gonna try every direction," before it turns around and tries something else, and then it's gonna try the block next to it for a few minutes, so it's got that motivation of goal direction, um,
Mhm.
and it's interesting to look at the balance between the exploration, because now it's looking very hard at how everything works right here, it's really in this curiosity and how do things work, um, uh, versus maybe it's still so goal oriented or something that it's trying to work very hard in this direction rather than accepting going up and around and in ways it knows how to do and then moving
Mhm.
forward.
Yeah,
It's
exactly.
a relevance, right? How relevant is honeycombing the ground versus walking over it to get to where I'm supposed to go?
Yeah, exactly. And sometimes, there it's that, like I said, it's that balance of exploration and exploitation. It, it's learning how to move around and operate in this environment. And actually, hold on, because we have a suggestion. A mode display on the right, for example, state showing for curious or explore. Ah, yes. So let me show that a little bit here, because right now I just have it on you where we can only see what its plan is. Right, the green arrow is what plan it's going to do. It doesn't. It should show the action. That's a good suggestion, but currently it does not. But I can switch its mode, and we can look at all of these red lines are where it's predicting it will end up, depending on the different action that it performs. So maybe like moving in a particular direction or jumping in a particular direction. We can kind of see these prediction lines of what it is, where it's expecting to go from a particular state. And these are getting a little more, honed in. At first, they were just very broad, like I think I'm just going to move on a flat plane. But now, as it's seeing that jump, there's the variations in what blocks are above or below it can affect the third dimension of moving up or down. And so we're starting to see like these angular um, directional arrows, and so the right now it's kind of in explore mode, so all of the arrows are red because it's not 100% confident of what these results are going to be. It's just, I think this is what's going to happen. But as it gets down to places where it has been, you can see some black lines show up, and the black lines represent these are things that it knows it has a very high confidence are going to happen. When it moves in this, it uses a particular action from a particular state. And actually, there we go, filter that down a little bit. Oh, and then of course they go away. But when it has these perfect, what are perfect matching, right? The block configurations around it perfectly match one of the rules that it has made. It's expecting that outcome will be the case next time that it performs that particular action. And so it doesn't necessarily mean that it's a guarantee that that's the outcome, because there is that variation in the lag inputs and the slidiness of the Minecraft movement. But it is fully expecting that is what the result will be when it performs a particular action. And if that's different, like if it happens and that prediction fails, it will update and create a new rule, and then it will be more confident about it the next time. So yeah, there's some really interesting dynamics there from what it thinks is going to happen and what will actually happen. And it gets pretty busy. The visuals get very busy at this point because a lot of its predictions are still very inaccurate. It hasn't really refined these predictions down. So
Yeah.
eventually, yeah, go ahead.
I was gonna say that you can see some of the training or the learning that happened at the bottom of this pit starting to pay off, right? Like now it's like, okay,
Mhm.
I'll go backwards from my goal because I know I can jump up grass blocks and I think that that will lead me to something more known, right?
Hmm.
It
Yeah, and as it's kind of explored off this way and found just a wall that it can't really make any progress, and it explored off this way and found, hey, there's a path up here. Like there could be a path up here, um, and I need to explore that and see what actions I can do to get up back up to where I want to be. And and so eventually, at this point, eventually it will figure out because it's kind of found its path forward, right? It's found
right.
a potential way for it to get up, and it will explore and it will find a path, and it will, carefully walk around the edge of the pit, and it'll fall down in the pit a couple more times as it learns, what it can and can't do. But it does eventually learn, okay, I can get around this pit, and I can continue forward. So
So we have a
I'll
we have a
do a couple
question.
questions here while it is
Yeah.
while it is
Singular volunteers are
learning.
asking if a similar AI
Let's see.
system will
Okay.
be I'm muted. Oh, no, I'm not. There's a question from the SingularityNET volunteers channel about whether this AI system will be integrated in Sophiaverse, the question I asked before we hopped on the air. And will AIRIS also be integrated
Yes.
into OpenCog, into Primus, and to all these components as well?
Yes. There is some there. We are currently working on integrating this system into Sophiaverse. This will be one of several systems that control how the characters interact with the environment and learn through these interactions and move around and kind of do the same kind of curiosity driven exploration and mess with things in the Sophiaverse AI lab and see how tinker with different things and see how they work and learn how to operate and what it can do inside Sophiaverse. So yeah, that is definitely one of the ongoing works that we are doing. Um, the the other question of will it be integrated into Meta? Yes, Patrick and Peter, who are working on NACE, which stands for Non-Axiomatic Causal Explorer. It is kind of like a an offshoot of Iris, if you will, that incorporates NARS, the non-axiomatic reasoning system, incorporates aspects of NARS and combines it with the Iris system to see how NARS and Iris can interact in useful ways and maybe expand that reasoning capabilities a bit and make it work a little better. And part of NACE is a meta bridge that that uses meta. And so we can communicate with the agent to give it objectives through meta and have it um, understand when we are communicating with it based off of its own experiences in the environment. So when it's interacting with different things, um, and it's learning, okay, I can push this ball around. This ball, and there's this other object that's like, that I can push the ball into, which is a goal, and then it's like, okay, that was my goal, and I did my task, and then it'll explore more ball, take push more balls into goals and things. And then we can talk directly to using meta. We can communicate with the agent and give it a different goal. We can say, okay, don't push the balls. Try and push the goal into the ball instead of the ball into the goal. See if you can do that. And it will explore and try and do that. And maybe it can, maybe it can't, depending on the environment. But using meta to not only communicate with the system, but we are also working, and this kind of, I think, follows up on another question of where is the data stored, right? Um, and what we want to do is we want to store the knowledge that it is gaining and the experiences that these systems are having in the knowledge graph of Hyperon and use meta and as well as all the many different algorithms that we have that interact with this knowledge graph and can process information, abstract out higher level concepts, do higher level reasoning, those algorithms will be able to utilize the knowledge that these experiential learning systems are filling into this knowledge graph, and be able to abstract out interesting ideas and plans for the agent to perform, to perhaps achieve a goal, or perhaps to even refine its knowledge some more and add to that added a higher level curiosity than just the kind of low level curiosity that the system currently has.
That's interesting, and it seems like Meta would be a natural, language also for writing and rewriting these rules and then being able to evaluate across them as well. So the agent can be updating, can be learning, can be adjusting, and then, making these predictions based on it. We also had
Mm-hmm.
somebody asking, and I'd be interested in this as well, if you can also train the agent. Can you combine some sort of, exploration, experiential learning, and training as well?
Yes. So it's not currently configured. It's only configured for self play. So it plays. We can change its goal at any time. We can give it a different goal. We can tell it. In this example, I have it trying to get to that little diamond block, but I could effectively move that diamond block to anywhere else in the world, and pick up the agent and drop it somewhere else and have it try to navigate towards any arbitrary place in the world. The other thing that it can do is just have no goal. We can just give it no goal whatsoever and just let it freely explore. Wander around the world, try and find things that it hasn't seen before, try and experience new things, learn new rules. It'll fall into these holes like it has here, but instead of trying to get back out of the hole, maybe it will go deeper and find a cave and explore out the cave system, because it doesn't have a particular objective to where it wants to go. It's just trying to see stuff it hasn't seen before, which is a very interesting experiment that I've kind of played around with, and it's kind of fun to just see it wandering around almost aimlessly, because as it explores, it does try and find more places that it hasn't seen before. So even though it might run into like a tree wall or something like that, or fall into a small hole that it sees everything about that, it will then try and get back out of that hole to go to areas that it hasn't seen. So it's a really interesting dynamic that's kind of mesmerizing to watch.
That's
But as
interesting,
far
a specific space of a goal to move towards versus just having curiosity, understanding what I don't know yet as the only goal, directing, and how much does that keep you in one spot, honeycombing the ground with with one cave versus going off somewhere else entirely new and learning about that. That's a very, interesting dichotomy there.
Yeah, and you know with the system as it's currently at the current stage of development, only being able to move around the world, that kind of limits what we can do with it. It's kind of like, okay, well, you can freely explore. You can go from point A to point B. You can, maybe the point that you stick is out in the middle of a deep ocean, and it has to, try and swim out to that spot or something like that. But as we are developing this and providing more development time to this and adding to its capabilities, like being able to place blocks, being able to mine blocks and things like that, we're going to see a lot more potential use cases for it. Like we could tell it to build us a house or something like that, and it could figure out what a house is, and have to figure out, okay, maybe it has explored and found a village, and so it sees a village, and then we say, okay, well, that's a house, and then it's, oh, okay, you want me to build something like that, and then it'll place little block, make a plan for placing blocks and stuff. So there's a lot of really interesting longer term research that we are working on. But even just this dynamic and adaptive navigation is something that has very practical potential use cases for a lot of real world applications, especially in like
Again, if
robotics.
my Roomba could find its way out of the the corner of the room, that would be amazing, and not go back there repeatedly, right? If it could sort of start to understand, which, a very small application for sure. But being
Mhm.
able to interact with these agents that have their own goals, their own motivations within a Sophiaverse, within a Minecraft, and to be able to, I mean, Mr. Horace says, "Come on, Agent Chan." We believe in you, almost there. We're rooting for this agent, right? This is just an AI curiosity model, but it becomes exciting for our own mental processes to watch this learning unfold, and we anthropomorphize that and make it personal and exciting that way.
Yeah, exactly. It's true. Like as I watch this and as it's exploring, I'm always like, no, 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 don't go back that way.
You're
What are
at the
you doing?
trees. You're at the
Turn
trees. Yeah.
around.
Well, and then it looks like it got turned around again. It's like, okay, finally I'm up here. I kind of know this space, and but my goal's over there. I better explore
Yep.
that way, back in the hole a little bit more.
Exactly. And as it's kind of building out this state space that of its knowledge, it's getting these more longer term plans. It's like, okay, well, like I can hop up there and I can go over there and I can, move in these particular ways. I'm expecting to be able to do that. So it can make longer term plans to be able to get to positions that it's curious about. And sometimes that works and sometimes it doesn't. But every time that it is analyzing this, it's like, okay, I really want to get back up there. So I have to, perform this sequence of actions to be able to get back up there. And it's kind of interesting to watch it learn, and because it not just doesn't just learn, okay, it's this set of actions. Sometimes the results of its movements, like right there, result in a different outcome than it predicted. And so now it's like, okay, well, now let's explore from here. Let's see if I can move around the edge, as it's starting to do. It's starting to figure out, hey, I can get around the edge of the hole here. I'm making progress. Oh, I fell back
But
down the
maybe
hole.
maybe not at the cliff. It's so funny too to look at the agents, my perception. I can see the broader world and perspective where it's only looking at these small pieces. If I could only see the small pieces it's looking at, I would probably chart a similar course where, I wouldn't have gone so close to that edge because I saw the big drop off below, which it was
Hmm.
unaware of at that point. So how does
Yeah.
this, so the amount of rules that the system has to create, get large, especially when there can be multiple actions and multiple environments and so many situations. How does this balance with the data efficiency that can be achieved with an AIRIS system for training and learning and understanding environment versus reinforcement learning or other techniques?
Yeah. So the data efficiency, the training efficiency of this kind of system, and the adaptability of it really puts it a step above reinforcement learning for this type of a problem, because it is able to quickly learn and adapt to new information, do this kind of exploration, and in a goal driven way. We're telling it we want you to get to this one particular spot. So you can imagine, a little robot in the real world be like, hey, my Roomba, I want you to go clean my bedroom. You're in the kitchen. And it would, explore out and figure it out and then remember that information so that next time it's like, okay, I'm going to move, I can move in these particular ways. But maybe you moved your chairs right in your kitchen. Your chair got left out, moved around or something. So now there's a new obstacle in the way. And it knowing how to move around these obstacles, it doesn't have to brute force its way through like bumping into it until it finally makes the connection to figure it out. It can know, okay, there's this new object in my way. I know I've bumped into chairs before. I know how these chairs work. I know how to move around this and get around this chair to be able to continue on towards my goal. And that kind of dynamic learning and continuous adaptability is really what is the game changer when it comes to applying it into more dynamic situations than just grid rolls and like in Minecraft.
And it's the Roomba's the toy example that we're all so familiar with, or many are. But of course, the same problem applies to we've struggled with Grace or other, care assistant robots. or any of the home robots, but navigating a hospital, navigating a home, navigating the objects there, so that a robotic assistant can navigate successfully without breaking itself or objects or causing problems. I think one of Ben's I don't know how seriously proposed replacements to the Turing test for general intelligence is the coffee test. You know, can you place an artificial intelligence in a kitchen and it makes coffee? You know, any given kitchen, right? So it needs to understand I need hot water, and therefore I can use a pot or a pan or a Keurig machine or the hot tap, or you know, like, and it needs to understand all these methods and opportunities, and then I need to find the coffee and I need a scoop, and that can be in a drawer or you know, it can be in all these places, and being able to navigate through an understanding in unknown situations is an intelligence. The Roomba just bumps into things, and that's as much intelligence as it has. It doesn't have this visual processing center to remember situations and states and novel or remembered experiences.
Yeah, yeah, exactly. And then, you know, the ability to stick, like this Minecraft is a perfect example, right? I could teleport it to anywhere in the world, and it could navigate and figure out how to get from one spot to another, never having seen that place in the world before. And be able to do the same with a robot in the physical world, to be able to have it where you could drop it into someone's home and it could map out the home and know where different things are, and as those things move, because they will, we're you know, we're living creatures, we move stuff around all the time, we rearrange the furniture, we put our keys in a different spot instead of, you know, where they're supposed to go or whatever like that. Its ability to update and know these different variations uh, makes it ideal for adapting and dealing with this kind of uncertainty, because it's not like it's just a snapshot. This is what the home looks like. Now you know how to navigate it, unless somebody moves something. It's constantly updating its information and constantly seeing these new observations and saying, oh, okay, the keys are on the table instead of on the hanger next to the door. So if my user asks, where did I put my keys? Oh, they're over on the table. You know, it can know these differences in its environment and adapt to them. Oh, and one more thing about the coffee is NACE. I love that Patrick kind of did a nod to this. In one of the NACE examples, I don't know if he showed it at the AGI conference, but in one of the NACE examples, he had a coffee machine, right? He had a coffee machine and a coffee cup, and it had to move the coffee cup over to the coffee machine as one of its goals of, you know, being able to make coffee from having no prior knowledge about how any of that stuff works. So that was kind of fun. I enjoyed that.
That was fun. I think he did. I don't know if he showed that in his keynote, but in the OpenCog demo, he definitely did. I can't recall about the keynote because I remember the OpenCog demo so well. We're back at the trees, agent. You can do it. And it's funny how fixated I become on the goal as well. Like, I feel like he needs to get to that diamond, and exploring this hole isn't good enough, right?
Yep. Yeah, exactly. And you can see
Um,
where it's like, oh, go ahead.
no, no, go on.
I was going to say, some of its actions, like where it's like, oh, I wonder what will happen if I jump straight towards the hole. It's For us, it's very much like why would you do that? You know, you have a pretty good idea of what's going to happen when you do that, and you're going to end up in the hole. Why would you even like think to do that, right? And that's one of the limitations of this system, of this curiosity-driven system in its current form, is that the curiosity that it has and the motivation and the reasoning that it has is at a very low level. It's like, okay, yeah, I haven't moved towards a hole in this way before. I'm not sure exactly what will happen, and that's as far as it goes. Like, it doesn't try and abstract the concept of a hole and that you will go down and that going down is bad and so you should not do that. And so that's kind of what we're trying to work on and develop by not just with Iris alone, but by merging it with Hyperon and with Meta and with these other algorithms that can do higher level abstractions and reasoning, to be able to help the system and guide it away from doing things that would not necessarily be the best thing to be curious about. Because an example would be, your Roomba might see a new obstacle of your cat in the way, and it might be curious, hey, what happens if I vacuum the cat? I haven't done that before. Let's go vacuum the cat. Well, you don't want it to vacuum the cat. That's a bad outcome. So
That would not work. Yeah.
yeah.
We had
So
a question. I'm sorry. Go on. I was just gonna say we had a question on this, so I'm glad you're addressing it. Somebody was asking whether the agent has the ability to forget situations it encounters that are no longer novel, and is it generalizing block formations in an abstract way? And you're saying not yet, and that's a key goal.
yeah, and so for the rules that it is generating and these low-level predictions that it's making, it is abstracting out information about like the configuration of blocks. Like for example, as it experiences things, it says, okay, there could be a stone block or a dirt block or a tree block off to my left, and that won't stop me from moving forward. I can move forward even though those blocks are there, as long as there's air blocks in front of me. I'm okay, and I'm expecting to move in a particular way. So it is kind of doing that really, really low level abstraction for its predictions. But the planning process is where those kind of abstractions are missing and are needed for higher level reasoning and higher level abstraction, and higher level goal planning, to be able to and instead of having to search across all of these different states, it has all of these states that it is searching across, to be able to say, okay, I don't need to search these little white boxes because these little white boxes are down here and who cares? I need to be searching these white boxes up here instead. And to kind of like narrow its attention and narrow its focus onto the potentially more relevant exploration rather than just the broader big picture exploration.
Yes, so we have this curiosity module, which is very exciting, and we have some directions for inference within OpenCog and NARS and others. But this relevance, that's going to be an exciting piece. I look forward to seeing the paper published on the relevance module for next year's AGI conference. So there's a question from Dan. Is there a bad actor tool being implemented to prevent saboteurs from corrupting the LLM? Stan, I'm not sure that there's an LLM involved in this, but I would be interested in Barrick's reaction.
Yes. So, and this system is there is no neural networks, there's no LLM, none of that is utilized in this system. What you can think of this as if you've heard of a finite state machine, it's like a finite state machine, but it's a dynamic state machine where it is building out all of these states from its experiences and processing information across all of these states, like we would manually code into a finite state machine, or like we would manually code into traditional expert systems, traditional AI systems. Like in video games, this would be governed by a behavioral tree, which would, and things like A star pathfinding and D star pathfinding and stuff like that, to be able to learn how to use, and it's not really learning, to be able to navigate in these environments, utilizing information that we are hard coding in and providing to these systems to calculate. And so this is doing it in the same kind of calculations, but in a dynamic and learning way. So there's no no neural network. There's no like I said, there's no LLM. This system, in the way that it makes rules and learns and does all this, because I'm able to show exactly what it's thinking, how it's processing all of this information. It's 100% transparent. And so it's a pure white box. It doesn't have any of the black box elements of traditional neural networks or LLMs, where we know that it can do this. We don't know how necessarily it's doing this or why it's doing this. We just know that we put some inputs into the system, we get the outputs that we want out of it, and then magic happens in the middle.
Absolutely. Um, it's also interesting to see. This reminds me watching the Mars rovers types of bots as well, right? It's human controlled, but it's moving very carefully, right? I'm going to try this before I move further than that. I'm going to try this before I move further than that, right? It's very much more interested in mapping the environment than the goal, and it's creating a very things that we would skim over as humans would be like, oh, that's a hole, I can go around it, and not learn about what's in there. It's going to learn all about that. It's going to learn all these pieces, and when it finds itself in a hole later on, it will have mapped that as well.
Mm-hmm. Yeah, exactly. Because one thing that it's hard to it's easy to watch this and be like, that was just a boneheaded move. Like, why would you even consider doing that? But we have so much experience and like common sense understanding and common sense beliefs about the world that we can apply to these situations that allow us to be like, okay, well, it doesn't matter if it's Minecraft or some other game or something like that. If there's a drop off in front of me, I'm not going to be able to just walk off and float through midair. I have to figure out a way around this, and essentially it's kind of having, it doesn't have any of that prior knowledge that we do, so it's having to learn all of that. It's having to make these rules so that it can understand that drop-offs are bad, and eventually, like, once again, this has only been alive, quote unquote, for about an hour, and so it has very, very little experience with the world at this point, very little, especially compared to us who have had years and years and years of experience, or even children. A baby, uh, for example, who's been alive long enough to be able to be mobile, a couple of years or a year or so, to be able to be mobile. You keep the baby away from the stairs because the baby hasn't learned
Right.
that stairs, it could fall down the stairs and potentially hurt itself. Um,
Right.
these are the kinds of things that happen just over more and more experience of our lifetimes.
Oh, I was curious. I had a question, and I got distracted by the baby analogy. Oh, earlier on we saw the mobs, we saw the animals, and it didn't seem to test or navigate towards them. Why was that?
Yes, that is because they can't see them. So right now, its only inputs are the, like the positional data of where it is and the block names that are around it. So when cows or pigs or wandering traders or something get into its field of view, it can't see them at all, which actually makes for some very interesting interactions sometimes, because sometimes down in this hole, a cow or a pig will join it, and the cow or the pig is also kind of hopping around trying to get out of the hole using its own little AI and blocking the agent from being able to make the movements that it thinks it's going to do, because it thinks it's going to jump up on this particular block, but there's a cow in the way, so it jumps and bumps into the cow and falls down a different way. And so it has to adapt to this invisible thing that is blocking it. It doesn't know why it's not, these actions are not turning out the way it thinks they should. It just knows that they are. And so it has to adapt and try something else and be like, okay, I think I can get around. Oh, I fell down again. I think it can get around, this particular block, because I can't seem to jump up there anymore. And then, oh, wait, no, I can jump up there. Why couldn't I jump up there before? I have no idea, but now I can. So that's great. I'll continue to think about things from there.
So
So there's definitely sometimes
it
that
will
I've
make
run this,
rules.
ran this.
It's making
Yes.
rules about things it
Yep.
can't see, and it's making faulty rules because it just can't tell that there's something. I've felt like that in life before. I've definitely felt like that in life before, where this should work, and why isn't it working this time or last time? Maybe rules aren't as helpful.
Yes. We had, that's programming in a nutshell right there, right? It's like, I wrote this code, it worked before, now it's not working. Why is it not working? We got some hidden semicolon somewhere that's causing it to crash.
Yeah, I love it.
Well, it's getting a
The
little bit
interesting
more
thing too I
complicated.
noticed is that for a human, there often comes a point where it's like, this isn't working, and I'm going to try something different. I'm going to go backwards. I'm going to go like completely different. And this agent is more interested in staying focused, on exploring what it does know, and variations, just to a limited degree on that, rather than something totally different.
Mm-hmm. Yeah, and that part of that is because it is kind of, we've given it a goal, we've given it a drive to move towards something. Um, the the exploitation of the knowledge that it is doing is kind of driven by that. It's trying. There may be faster or more effective ways of jumping from one of these states to another state, where sometimes like it'll try and get from one state to another in a very convoluted, wrapping around a whole different, go down here and then over here and then over here, then to get to this, when it could have just stepped like one step to the right to be able to get there. And a lot of that is just because it has this goal. It's like, I need to get to this diamond block. I need to get to this one spot in the world. And I know how to get to this. I know a way to get to this, to where I want to continue to explore from. But it's kind of convoluted, and maybe I could shortcut it by doing, this other action, but I don't know if that's going to result in that. So I'm going to go with what I know, and and try and use that information as much as possible that of what I've experienced to kind of push my knowledge a little bit further in the direction of my goal. And
as you said it.
yeah, and when it's in that more like the free form exploration, that's when it gets more interesting as far as finding these shortcuts, because it's like, okay, I want to get to this particular state because I think that there's some exploration to do there, and it will be like, okay, well, let's try and get over there, and I think it'll happen this way, so let's try that. And it's not quite as narrow-minded as when it has a goal that it is trying to do.
Are you able to dial modularly between the goal and the exploration, or is it one or the other?
Yes. So there are definitely, it's kind of like when you're doing heuristics for searching a state space, then you can tweak how you are searching, whether you're searching for new information or whether you're searching for goal-driven information. And so, yeah, there is a potential there to, you could have like a little slider where it's like, okay, tweak it more towards exploration in real time. And they're like, okay, now let's slide it over here and see how you do, and see how that affects things in real time. So we can modify its planning, we can modify its reasoning as it's doing things, and as we're observing its behavior and seeing what it's planning, to be like, well, you're beating your head up against a wall for no reason because you're so focused on moving towards your goal. So let's dial that back a bit and let you kind of explore more um, find out more information. And so right now for this particular demo, I've found kind of a nice little sweet spot for it. It's not perfect, but it does a pretty good job of balancing between exploration and exploitation. Because there's been times that when I've been messing with the planning, where finding a way out of this hole has taken it 7 hours of just beating its head against every single movement and every single prediction. So it was on very much explore mode, and it was like, okay, I'm going to explore everything about this hole. And it took it so much more time than when it was more focused on trying to just get out of the hole and move towards its goal.
That's really interesting. But are there specific directions that you're looking at for abstracting that knowledge? That cliffs, holes will always fall down, no matter if it's 2 blocks down or 3 blocks down or unknown blocks down. Are there goals and methods for doing that you're looking at adding, or is that an unknown?
It's kind of an unknown at this point, but we kind of have an idea of what we want to do. Things like PLN, to do that kind of abstracting out of these rules and figuring out the different aspects of it. There's stuff like kind of like collating the results of a particular action in a particular thing. So like if if it has a prediction that it's not 100% on, it can look and see, okay, in these rules that I have, if 9 outcomes out of 10 result in me falling in a hole, then I need to take that into account and assume that I don't know exactly what the outcome is, but falling down is one of the outcomes. And I kind of want to try
Edge of
something
my seat.
else. Oh, yep. And now it's finding itself even deeper down there. So now it not only does it have to explore, but it has to explore its way back up to the places it's already seen. So it's adding more information and mapping out more information as it goes.
It's so interesting too. I mean, this environment, as you say, it's much more complex than a grid world, but it's much more simplified than a real world, right? There's nobody's, moving chairs around and such, other than the invisible critters that it can't see. And there is so much for it to learn and for it to explore. How do you see the long-term payoff of this system, after it's gone somewhere, found the diamond, spent 7 hours in a hole exploring, and really understands? I mean, it'll understand that hole, but it will also understand more about holes generally, as long as they're not too novel. Does there come a point where it's like, yes, now it's learned enough to be super functional in the world, but now it has so many rules it's slowed down? Or, like, is there a balance there?
Yes, and that is, that's one of the concerns that I have with and what I want to kind of explore with just letting it do like that free form um, exploration, right? Just letting it freely roam around and find information, find places that it's learning and exploring and finding new places and refining its predictions to see, okay, if I give it a map, like a map-sized area of Minecraft to explore, and just explore every aspect, go down every hole, explore the bottom of every bit of ocean, like just explore the whole entire thing. What does that result in? Like, how many rules did that take for it to be able to fully understand and map out this area? And not only that, but then take and drop it another map over and let it fully fill out that. How many more rules did it have to learn, in order to, and how effective was it in, now that it has all of a map's worth of knowledge, how effective is that knowledge in filling out another map worth of data? So there's definitely a lot more experimentation that needs to be done, a lot more letting it run. One of the problems with it right now is that because it is only navigation and can't manipulate the environment, it's very easy for it to explore freely and get stuck in some hole that it can't get back out of. And so I'm kind of developing an automated process for checking for that. And if it is stuck, or it thinks it's stuck, then to, teleport it somewhere to safety so that it can freely continue to explore. And then if it comes across that hole, for example, again, it will be able to predict, I'm going to go down in that hole when I perform this action. I've explored that hole and I get stuck, so I'm not interested in going down that hole at all. I'm going to go somewhere else and explore somewhere else. So there's some really interesting stuff there that I'm working on, that hopefully I'll be able to set up and potentially do a stream of that. Just kind of let it run and let people see, what it finds and what it sees.
We'll uh, call it Truman and make it the Truman Show, and there's no copyrights because that's just its name, right? It's
Yes.
mesmerizing. It's mesmerizing, and it's funny to watch myself in looking. I find myself watching its map more than the Minecraft map, and its moves make more sense than they should. Like when you can't see the whole world. I would, but being on the edge of my seat and wanting to get out of this spot and not hit that particular hole again. It's very
Mhm.
interesting, very drawing. So the agent
Yeah.
has this. Would you? Is this decision area that we can see? Is this it? You were saying in your paper that it's an expert system. It's mapping against a state map. Is this the state graph that it's mapping, or is this just its
Yes.
visualization of its own map?
Yeah, so this is the state map that it is building. So it's building out this state map, and it's a very complicated state map because there's a lot of variations, there's 16 different predicted outcomes for each one of these states, and it has to try and map out. And what's interesting is that in the presentation that I did, said that there's like these disconnected goal substates that float around in the state graph from where it is that it's trying to connect to. And in a dynamic environment like this, we have that same situation because all of those black states that we're seeing right now are unconnected to where it currently is. So it's
Right.
almost like it's creating multiple graphs, multiple subgraphs that are
Yeah.
all like little islands of their own. And then eventually one of these islands will connect to another island, and then it'll all be interconnected, and it can have, be able to search that whole space. Um, and so it's a multitude of these state graphs that it is building in its mind, and exploring in real time, and interconnecting these. And some of those connections can happen not from direct experience, but from learning something else somewhere else, where it jumps in a particular way. And oh, well, if I jump in this block configuration, well, way back over here, there's that same block configuration, and that connects that. Well, that ties that state to all of these states, and then it, all connects it together in its mind, even though it hasn't actually done that particular action from that particular state. It's able to make predictions and connect all of these predictions together.
This is both an overlay of its map. I've mapped the world, and here's what it looks like. And at each point is, the 16 directions, the 16 connections that it can make between blocks. And that's what it's both overlaying. Where am I at on this map in relation to a grass block, a rock block, a tree block, and where am I at on my physical reality map in connection to the diamond?
Mm-hmm. Yeah, exactly. And so here it's predicting that it's going to move in a particular way, and that prediction is going to tie into all of the rest of its states. And so it's sitting there and it's thinking as it's processing out and exploring, bam, all of these different states, and all of these different predictions. I mean, each one of those is a prediction. So it's a lot of data for it to process. And right now, it's not doing it very in an optimized way. It is just running on a single thread CPU. It's not like it's doing any kind of multi-processing or parallel processing to be able to do this search space. So there's so much optimization potential that is yet untapped and unexplored. Um, Being able to run this on a parallel system where it could explore out these state spaces all, as in parallel rather than, one at a time. That's a huge optimization that will probably make it run significantly faster than it already does.
So you're saying that when it comes time for this implementation of Sophiaverse, it won't look like this. We won't see Sophia jumping into walls and into holes for for 10 minutes at
Mhm.
a we
Yes,
had a
yes,
question.
exactly.
We had a
And
question.
yes, go ahead.
No, no.
I was just going to say, the Minecraft world, with all of its dynamic blocks and three-dimensional movements and all of that kind of stuff, is very different from a lot of other environments, right? I mean, if you think about like the real world environment, like with our houses, we pretty much just have a flat plane, maybe some stairs that go up and go down, some things like that. But it's a lot less three-dimensional movement than we would have to do as if we're like trying to climb a mountain, in the real world. And so a lot of the heavy processing, the heavy learning, the heavy planning and stuff is simplified just by the nature of our own intentional simplification of our environments. We make nice flat floors and nice carpeted areas so that we don't have to walk around on grass and dodge stones and all of that kind of stuff. We manipulate our environment to make it easier for us to live. And those same kind of manipulations also work well for a system like this.
Absolutely. We had a question for the link to Patrick's NARS paper and how the system is being combined with NARS for the corvids in NACE. And perhaps our moderators can link the paper, but can you talk a little bit how the system's been adapted for NACE in the systems that they're building?
Yeah. So the core system that NACE is built off of is the original grid world system that I built for IRIS to demonstrate kind of like the beginnings, the potential of what this system could do. And so when I built that, I worked. Patrick reached out to me because he and I had discussed things in the past, and was very interested in this real low level curiosity driven exploration, because that was something that they were having a lot of trouble with NARS. They could do a lot of the high level reasoning and high level understandings, but when it got down to like the nitty gritty low level stuff, things were kind of breaking down. And so the idea was, okay, we have NARS, which is this kind of higher level reasoning system. If we combine that with something like IRIS, like with what he's doing with NACE, as we take this experiential learning system of the low level rules and then combine it with the reasoning of NARS, then we can get that we can start to bridge that gap of the better understanding of the world and the better planning and the better goal-driven curiosity that the system currently uses. And it made it. It got out of the hole. Woohoo! Yay!
Good job, Agent Chen. We're rooting for you. I don't know how we
Yes.
Agent Chen, but I like it.
I like that, Agent Chen. Yeah, so it finally found its way out of the hole, and it's heading towards its objective. So good for it.
Which again, 20 minutes of life, not bad at all. Very impressive. My gameplay learning on Minecraft may have been slightly faster in some ways, but maybe not. So I probably wouldn't have explored the hole quite that long.
Yep, and that's true, and it's kind of like you brought up a good point that if we had to play Minecraft with as limited of a view as this agent,
Yes.
how would we play Minecraft? How would that affect how we play Minecraft?
Yes.
And I actually think that would be kind of a neat mod to put out there. Just a limited view version of Minecraft, just to kind of compare to see, okay, how would a human play? How would a human approach the same situation in the same environment that the agent is currently experiencing?
Right.
Because
right.
I think that if it had that long view that we have, it would probably be able to make more accurate predictions about what's going to happen if it was to try and jump back down the hole.
Yeah, I don't know if I'm at the edge of the hole yet, or if I'm on a cliff, or I don't know if I'm on dry ground now or at the edge. Yeah, it has no idea, like I can see. So absolutely.
Yeah, exactly.
So we've talked a little bit about some of the applications, right? We've talked about the games, the NPCs, Sophiaverse. We've talked about mind children and personal assistant robots, coffee making, Roombas. We've had some great suggestions from the watchers, from the commenters, about other potential applications for this, exploring the seafloor, again, not unlike exploring Mars or other extraterrestrial objects, or saving surfers with drones, right? Just being able to navigate, use a drone to be able to navigate and watch for patterns elsewhere. What other real world applications do you imagine or envision that this could be optimal for?
That's a very good question. There are, the way I kind of look at it is there are some limitations to the system, just to be clear, that make it that reinforcement learning does better at. One of the limitations of this system is the ability for it to understand that not everything that happens is because of what it is doing. So once I give it the ability to see the animals and to see the cows and stuff moving around, the first thing it's going to do is think that, okay, I moved in this way and the cow moved that way and the cow moved that way because I moved this way. When it doesn't, they're not connected at all. They're completely different rules that govern completely different things, right? And so we haven't yet found a great way of breaking that connection and building like two different rule sets for two different or for multiple different things, so it can kind of build its own rule set about a cow to be like, okay, if I hold up wheat, the cow comes to the wheat. That's a rule set specifically to a cow. That doesn't apply to a pig. I have to hold up a carrot for a pig or whatever. And so there's a lot of things like that, especially in like even just in simple 2D environments, right? Like Atari games. Deep learning is very good at learning how to play Atari games. It takes millions of episodes for it to learn it, but it can learn it and it does it very well. We don't think that IRIS or NACE can necessarily do that yet, but what we're learning is that it doesn't have to be able to make predictions and predict the movement of like a cow or say like if you're in Space Invaders, the movement of the little aliens on the top there. It doesn't have to be able to make an accurate model or be able to predict the movements of those to still be effective. It can just adapt to that. And as Patrick demonstrated in the workshop at the AGI conference, where he added his own avatar into this grid world. So he and his little corvid raven were interacting in the same grid world, and he was moving around, and the AI was moving around, and one of the things that the AI was it was curious about him. It wanted to see what happened when it interacted with him. And so it would try and chase him. It would chase him, or it would chase Patrick around. It would chase his little character. And even though it couldn't understand like the movements, like Patrick's movements, or where he was planning to go, or or his motivations or anything like that, it was able to adapt to his movements and be like, okay, you were there, now you're over there. Okay, I'm going to head towards you now. Oh, now you went over there. Okay, I'm going to head towards you that way, and kind of chase him around the environment. And even when he like hid around on the other side of walls and stuff, the agent was able to plan a path around the wall to get to where he was. And so there's some more experiments that I want to do on that front, especially when it comes to like the Atari game worlds. Because for me, when I was developing it, I thought that it would need to be able to model those types of movements and understand those. I didn't even consider that it was adaptable enough to just work with that dynamic environment rather than trying to accurately predict everything that's going to happen. So there's definitely some more room there to explore. But at the moment, that is where like things like traditional reinforcement learning and deep learning do a better job, is understanding and being able to predict those movements of other things and how those other things do things in the environment, to be able to move the little character at the bottom to shoot the UFOs more accurately and do a better job of that. So it's kind of interesting.
It is interesting. That's very interesting. So our agent is very open-minded and curious, open-ended, happy to explore a hole for hours, or honeycomb the ground just to see what block is under this block, but fairly self-centered. That doesn't have a theory of mind. Can't
Right.
see or predict what's happening over there. But you're saying there may be interesting ways. Well, Patrick has Hammer demonstrated some of his methods
Mhm.
of working with that, and
Mhm.
perhaps trying to get around it. Was that part of the NARS system, or how did he? Do you know how he worked with that?
I think, well, because NACE utilizes parts of NARS, so I'm not 100% sure how much of that was like the NARS understanding and how much of that was like the NACE understanding, but I'm pretty sure. Oh, it made it to its goal. It did it. Good for it.
Yay! Congratulations, Agent Chen. You
Yay!
did it.
All right.
Diamond block for you.
Now, yep. Now it is teleported all the way back to the beginning, because usually when I do this, I just run it on a continuous loop.
Will it
Oh,
use
it
that
actually
same
teleported
pathing?
somewhere else.
Ah,
There we go.
would it, if
So
it
now,
had gone back to the beginning, would it use that same path, or would it develop something much
yes.
newer?
So yeah, it looks like I have it set to teleport over here instead. Whoops.
Nice.
That's okay. Now it'll just
This would
continue on from here and head towards its thing. So yeah, it will. It will utilize that path. Um, that path will probably update a little bit because of all of the experience it gained in the process
right.
of what is experienced. But it will mostly follow that path until something like it comes across one of the states being disconnected from the other states, and then it would be more interested in um, exploring and seeing how to get to there, because you can kind of see here where it's starting to like disconnect. It was moving alongside of it, and now it connected with its old history, and now it's just
Yeah.
exploiting that knowledge and like, okay, I can get over here, and then it will
That's very cool. So is this map that it's following actually connected with Minecraft? It's actually map like it didn't need to recognize where it was and how close it was. It knows its coordinates and how close it was to paths it knew.
yeah, exactly. So it's not a direct connection. This map of Minecraft that we're seeing here is just the blocks that it has seen in a particular position when it was in that position when it saw them. So it's
Okay.
not pulling this all of this map or anything from Minecraft itself. This is the internal map that it has built in its mind of the kind of like a model of the world as it has seen it in the past.
Yeah.
So we can actually take, and actually, well, that might be kind of fun to do real quick. Let's grab him. Wait a second here. Okay, I'm going to take him, and we're just going to dump him somewhere else. Let's see, where should we put him? Let's put him.
I like this suggestion from where's los.com it that the agent needs a digital cane, right? Feel off the edge of the cliff before it steps there.
Yes, yes, it does. Okay, so let's see where we dropped it. Okay, so we dropped it over here. And we can, like I said, we can just pick it up, drop it somewhere else, anywhere in the world, just randomly. I can teleport it around, or I can take control of the agent and put it somewhere else, just like I just did. And it'll just continue from there and be like, okay, I need to get over there. And how do I get there? I'll just make up, start exploring a path and building out this state graph towards that particular location.
And how would you
Go ahead.
how long would you predict? I could see how much more quickly the agent on that second and third run to the diamond, it was on a much shorter path, and I could see, when it went that same path again, it was quicker, but it also didn't have a hole in the way, which was convenient.
Mm-hmm.
If it had transported back to its initial starting point, how long would you predict it would take to get to that diamond the second time around on the original long path around the hole?
Yeah, that's a good question. It's about to find another hole. So
Excellent.
there it goes. Good
There
luck.
it goes. And water.
And water. Yeah, it has not experienced water before.
How does it do with dying? Is that incorporated in this Minecraft world?
It is not. So it is in creative mode. One of the reasons why, I mean, I put it in peaceful because, if it runs into creepers or it runs into, those are things it can't see. It's all of a sudden just dying for no reason. It's getting shot by a skeleton, an invisible skeleton. And so I put it in creative mode because it doesn't yet have the understanding that it has health. That's not one of its inputs yet. That's another one of the near-term steps that I'm going to be adding, is giving it health, and so that things like, for example, that might help with its reasoning of not falling back into the hole, because falling in that hole is going to hurt it. And
Right.
so it will be like,
Right.
okay, I don't want to
There's a
get hurt, so
cost.
I'm going to avoid that, and maybe that'll help with its reasoning capabilities. So there's some interesting stuff to explore there. Let's see. Let's
And this whole
do.
new water thing. No, that's interesting.
Mm-hmm. Yeah. So the water thing, the movement system for the agent is not really built to deal with water.
Yeah.
So basically, what it does is it's trying to jump and it swims, and then the system is doing the same thing as when it's falling, where it's just waiting for its movement to settle. So when it falls into like a deep ocean, it'll just sink all the way down to the bottom, and then land and be like, okay, here's where I am. Let's figure out what to do from here.
Yeah.
All right, so let's do that experiment real quick. Let's take it all the way back to its beginnings.
Okay.
And we'll see how long it takes for it to... Oh, by teleporting it, it got confused and thinks that that wall was right there. Yeah, that is a problem sometimes when
Interesting.
you're teleporting it around. It
Right.
because it moved from one spot to another. It's like, oh, now there's a cave where this was. That doesn't make any sense, but it adapts to it. So yeah, now it's got a
Yeah.
long form plan that it's tracing back along its path. But from its experiences, it's not 100% confident right here of what's going to happen. It thinks when it jumps from here, it's going to land here, and then it's going to have to move here, and then continue on. So the additional knowledge that it has kind of affected some of its predictions and things that have broken its path of what it's expecting forward. But it'll adapt to that, and it'll learn, okay, well, is that what's actually going to happen? We'll find out.
Right.
And if it is, then it'll move on from there. If not, well, it'll just get back on its path and keep going.
How long have you been developing the AIRIS system?
So I started work on it in 2016. It was when I first had the idea, because my background is not like academic or anything like that. My background is game development. Like that was my thing. I wanted to make games, so I made indie games here and there, just little fun projects and stuff. And as I was developing these games, and I had a game where I needed some AI in it to have some characters that did interesting things. And I was getting frustrated with the amount of work that it was taking to build the behavioral trees and to build all of these systems to govern the behavior of these agents. And I was like, well, why can't an AI system just learn these behaviors on its own? Why do I have to code these in? Can I do make a system that can build out its own understanding of the world based on the same kind of thing of like cause and effect relationships that we do when we're doing if then statements, when we're hand coding these rules. So that's what kind of stuck in my head, and for a couple of years before I started work on Iris. And then in 2016 I was like, okay, I kind of have an idea of how this would work. Let's see. And so I built out some very simple tests and some very simple agents. I actually built it in GameMaker Studio. I built it inside the game engine itself, rather than using like a more formal programming language, just because I was very familiar with GameMaker. I'd made a lot of games in it, and it was easy for rapid prototyping, right? And so I made this simple version, and it ran horribly slow. I had to let it sit for 2 days straight for it to be able to learn very simple grid world environments, and but it did learn them, and that was the spark that made me think, okay, there might be something to this. I need to build on that. And then for the next few years, I've left the Minecraft or the Game Maker days behind, brought it into Python, made some more environments, made some more much more improvements on optimization and running. And so it was there that and then I started doing like the generalization thing, because I chose Python as the language because so many AI systems and so many benchmarks and so many environments run through Python. And so that was my intention, was to build a system in Python so that I could easily connect it to these other environments and these other benchmarks, and um, see how effective it was at generalizing, not just in grid world environments, but across other domains. Like I showed in my paper and in the conference, the AGI 24 conference. Oh, now its path is all the way. It's learned its path. It's connected back to its path, so it is confident in all of the moves that it needs to make from where it's at, way over there, all the way bouncing down around inside the hole and coming out towards its goal. There, I'll just turn on follow mode. So in expanding into these other domains, I did the cart pole, which is a classic control problem of balancing a pole on top of a cart. That was my first venture into the whole like continuous movement, kind of random fluid space, and it did very well at that. I also did some very basic character recognition. Oh, watch out for the pig, where it could learn some of the handwritten characters of the MNIST handwritten character data set, and I was getting really good results from these as well. And I was like, okay, this there's some real good potential here. There, like I need to develop it more. I need to keep working on this. But of course, all throughout those years, it was not my day job. Right? I worked as I had a couple different jobs over the years, and at the time before coming on with SingularityNET, I was working as accounts receivable for a liquor warehouse, and that was my day job. And I had like a 2-hour commute every day, so I really couldn't focus and put as much time, attention, and effort into this system as I really wanted to. And until I was able to get on board with SingularityNET and be like, hey, you guys are awesome. The brains, the intelligence, the knowledge, the all of that, everything, it just connected perfectly. And I'm just so excited to be with SingularityNET and really pushing the envelope of what all of our combined brain power is going to be able to achieve.
Now it is your day job, so
Yeah.
that's amazing. Not only developing this AIRIS system, but actually putting it into something ambitious towards AGI Sophiaverse and Sophia's own growing, and other NPC characters' own growing toward their own intelligence. So now we've got a curiosity model that's very exciting to the team and integrates really well with the other components that we're working there. And we happen to have a language that's great for rule rewrite as well.
Mm-hmm.
So excellent. I like
All
this.
right.
Thank you for sharing all that. It's really exciting to hear how the necessity is the mother of invention, right? You needed something to learn its own state, so you didn't have to sit there hand coding it all day, and so you built something that's very novel and interesting, and there's a simplicity to it that's really beautiful as well.
Mm-hmm.
Looking at NACE, I mean, I think that boils down to just the four rules. Have I been in this space before, or let me seek the space with greatest uncertainty, and head towards my reward. And if I don't have any uncertainty, then I'm going to go back to where I haven't been in the longest and see if there's something new happening. It's a very simple distillation of how to curiously explore and solve complex problems as well. Very simple algorithm.
Yeah. And the nice thing about simplicity is having a simple system to build from puts a nice foundation for all of these other systems that SingularityNet has been working on for years and has matured so well, that are so capable across all of these different domains. And to have now a foundational level of learning to fill in the gap that had existed is going to result in some absolutely amazing work in the near future.
Absolutely. And I really appreciate too. Stan said that this is one of the most profound interviews to date. Thank you very much, Stan. But the real time access to what's happening here confirms the advancement and possibilities for AI. I don't think that it's quite clear to most lay people who maybe only, if they've seen AI at all, they've been introduced to ChatGPT or Alexa, just how fixed those systems are. You know, Siri, Alexa have some adaptability to what apps you have, and I don't know, the types of questions you ask and how you ask it in your voice. But actually gaining knowledge, or ChatGPT actually gaining knowledge from a conversation with you in order to have a better conversation with you in the future. That's just that real time access to learning is something that's been inaccessible for most currently available commercial AI systems to date. And it's so important here. It makes the system so much more agile, robust, and powerful. And as you say, in combination with systems that can help it understand cows and theory of mind and other things better, it's such a massive opportunity for a step up and improvement.
Yeah, absolutely. Absolutely.
So the SingularityNET volunteers asked if Neoterix will be an integration of another game or will be on Sophiaverse. First of all, perhaps our moderators can link. We've got a great PDF to the Neoterix paper on our website under our research area, I believe. But perhaps, Barrick, you can talk to the Neoterix and
Yeah,
how they become integrated with Sophiaverse.
absolutely. So Neoterix, that is one of Ben's core ideas that he's been wanting to do for a long time. And that is the idea of having these new digital people that exist in a world and interact with it and learn from it in a dynamic and adaptable and continuous way, just like what we're doing here with the Minecraft world. Of course, the idea behind the Neoterix is a little more complicated. We want these systems, we want these agents to not just be able to navigate from point A to point B, but to have their own drives, their own motivations, things that they want to do in the world. It would be kind of like putting this learning agent into a villager in Minecraft and having it so that it had to learn how to farm and trade and do all of these things with all like with the players and other agents and other villagers and stuff like that, and be able to craft things and go mine for resources and all of that. That's kind of like the idea behind the Neoterix, is to have these digital beings that are inside of a game world that are living in this game world and interacting with it as if they were a human interacting with the real world, just in a digital way. And the Neoterix are a very fascinating challenge, because there's so much more involved than just the learning that we are seeing here with Iris. There's also that higher level reasoning, the higher level planning, and figuring out, I'm hungry. I need to be able to get food. Where can I get food? I need to find where the cows are. Okay, I know where the cows are. I remember there was some cows over here, but I need to have, something to kill the cows. I need a sword. So I'm going to have to go mine, some stuff to be able to get the blocks that I need to craft the sword. And it's, the complexity of that is significant. And but I think that it is, as significant as it is a manageable problem, and we are moving quickly towards that. And the way that we're going to experiment with that is with Sophiaverse. One of the drives of Sophiaverse is the introduction of Neoterix into these environments. And even just the character of Soph herself being a proto-Neoteric, a beginning experimentation into this world of teaching these systems how to live in digital environments, and being able to then do additional experiments and put them into interesting situations and seeing how they adapt and interacting with them. And that's a key thing. It's not just, in this environment, here's this character moving around and exploring Minecraft on its own. It can't see anything else out there. If I was able to, drop in there myself as an agent, as an avatar running around with it, it wouldn't even see me. It wouldn't know I existed. All of a sudden, just blocks would be disappearing, or appearing to help it, and it wouldn't have any understanding or any kind of way of interacting with me as a player. Whereas the neoterics are kind of designed to be these, like, tribes of agents, with agents interacting with each other and learning and sharing experience and knowledge, and communicating in their own way, and interacting with humanity through avatars and things that interact with them, to see how they react. How do they have emotions? Do we need to instill emotions in them? Will emotions emerge from this complexity of intelligence? And so there's just so many interesting unanswered questions that we can start to mess with when we get to the point of having neoterics. Neoteric equals Ryan Reynolds movie Free Guy. Yes, exactly.
I love it. I love it. Yeah, and the complex interactions that they had too. Getting AI to communicate, learn to communicate with each other. I've got a sword.
Mhm.
You know where cows are. And be able to coordinate
Yes,
in a game world too.
yes,
And something
exactly.
that many people may not be aware of, but Sophia herself was designed to be not just this robotic ambassador, which is profound, right? The way that she puts a face to AI, and the future of AGI is a profound mission in itself. But she's also intended to be an AGI platform so that anybody could have a Sophia or a little Sophia, and use that as a test space for their own AGI-ish systems. And the same with Sophia Verse. Sophia Verse is intended to be a playground where anybody with AGI-ish ideas can go in there and test them, right? Like this Minecraft type environment, so that if you have an idea on a different inference engine or a curiosity model, a relevance model,
Hmm.
then you can go in here with your AGI into Sophiaverse with your AGI system or AI systems, and use that as a test bed, a sandbox, a play space. And the neoterics are part of that, something that can themselves learn and grow and gain their own intelligence in a very natural way, like you needed for your agents and your systems that generated this whole direction.
Yes, exactly. And it's also like we had talked about way earlier, this, like, sliders, right? The exploration versus exploitation sliders. These kind of hyper parameters of its personality, and what drives it, and what makes it choose one particular action over another. Being able to have access to these little knobs that to turn them, and see what combinations of these result in interesting characters that do interesting things. Having that ability to mess with it at that level, and experiment with it, and try, like, picking up your agent, and surrounding it with a bunch of blocks, and seeing what it does, and doing that kind of interactions, any kind of experiment that you can think of. I mean, that's going to be an incredible tool, not just for researchers who are interested in pushing the boundaries of the AI systems that we have now towards AGI, and specifically beneficial AGI, because there's also some elements there that were brought up during the workshop. What if, in Patrick's example of his little crow that was chasing around Patrick's avatar, what if you give the crow an axe? Like, will it try and attack Patrick
Right.
out of
I don't know what
curiosity?
happens when I apply a key to a person or an axe to a person, or
Yeah.
I don't know yet. I should find out.
Yeah,
Yeah.
exactly. And having those kinds of uh, interactive experiments to see, okay, we need to figure out a way of curbing that kind of potentially dangerous curiosity, because we don't want that in the real world. That would be not beneficial.
I wonder what happens when this car hits a, yeah, no, not good.
Yeah,
Um,
yeah,
and and that's always, I think that's always a debate too for AGI-ish systems, is how much do we need to hard code? Do we need to hard code gravity exists and your feet will be stuck to the ground and you don't need to worry about that part, or let it figure it out because it's sort of obvious. Same thing with raising children, right? Like
yeah,
you teach them very young, or don't hand them the knives until you can teach them that, this will cut, this will hurt yourselves or others, and don't, right?
yeah, exactly. And we need to be able to teach them these things in controlled ways, just like we teach children. So that our little Roomba robot, who's trying to make us a cup of coffee, doesn't melt its hand on the coffee burner.
Or go all cat on us and get under our feet and trip us, right?
Yes, yeah,
Stay
exactly.
out from under my feet, yes. I have a question going back, quite a ways. You were saying that you were able to utilize the system to train, character recognition on the MNES set.
Yes.
Um, I'm quite curious. I see it's very apparent what the state graph is for any of these 2D or 3D worlds that an
Hmm.
agent is exploring. What did you use for a state graph for something like that? Again, I think I've shared. I'm quite curious on how these systems might be applied to LLM conversation. How do we create curiosity in an LLM to guide its conversation? So what is the state graph for a non-game environment?
Yeah, that's a very good question. For the handwritten character recognition, it is basically just it's like a one state forward prediction. So it doesn't have to build any like large prediction graphs. It's just looking at, okay, here's the pixels of this image. What do I predict the label is? Do I predict it's a 1? Do I predict it's a 7? What's the closest match here? And so it's just a one-step prediction. There's no real state graph out there. It's just here's my current state. What do I predict the outcome of in this case revealing the label, because it starts off blank, it has a blank label, and then reveals the correct answer. I predict that when the answer is revealed, that it will be a 1, or it will be a 9, or it will be whatever based off of the rules that it has seen.
Okay, thank you. That's
Yeah.
extremely helpful. That's excellent.
And it to its goal again and got teleported away. Good for it.
Fantastic. It's obviously significantly closer. It still chose to go down the hole.
Hmm.
Again, it's I think one of the most fascinating things for me in this whole system is watching my own thinking, what I want the agent. Don't go near that cliff again. Don't,
Yeah.
fall in that hole again, and um while it's doing the thing, it doesn't care about the efficiency or lack of efficiency of going down in the hole. It knows a path through. It knows it'll get out again. Even if it's in
Hmm.
a crazy loop and not directly out, it
Yeah.
knows that will work, and it follows it. That's its efficiency. And that's
Yep.
so interesting to see.
It is for sure. Like I said,
All
it
right.
is very mesmerizing to watch.
Fantastic. Thank you very much. That's 2 hours, which I think is what we talked about. I thank everybody
Yep.
who stayed on for this long. This has been
Yes.
absolutely
Thank
incredible
you,
to see
everyone.
this in real time. Thank you for sharing this. Thanks for bringing this demo from the AGI 24
Mhm.
into all of the virtual attendees that wanted to see it, wanted to understand the system and what it's doing, and sharing so much about everything that you're doing here and how that looks for the future. So thank you very much, Barrick.
No, it is my pleasure. And if I didn't get around to your question, feel free to comment on the YouTube video. I'll go through and answer everybody's questions in the comments.
Thank you very much. And we'll try and link up again the GitHub where folks can get involved, as
Mhm.
well as your paper from AGI 24. And I hope that everybody enjoyed it. I guess the GitHub people can actually download and utilize and play with the system. Is that right?
Yes, they can run it in Minecraft. You can download it and run it right now. I need to put better instructions on how to get that up and running because it's not 100% clear. So I apologize for that, but I'll work on that. I'll work on that and get that updated so that you guys can get the Varia Minecraft mod running and be able to run Iris on your own.
That's perfect. Thank you much, Barrick. Thanks for all the time. Thanks everyone for being here, and we'll see